Hi there, it's Dr. Kalanko. So I just wanted to spend a little bit of time to give you a brief summary and kind of my perspective on NMR couplings, particularly relating to how to interpret aromatic couplings. So if you'll recall, coupling is a situation where we are getting information about what's on adjacent atoms, okay? So it allows us to determine connectivity by observing this degree of splitting that we get. Now, we've been talking about coupling in a pretty simplistic sense. There are a lot of couplings that are out there, but mainly we've been talking about coupling from one hydrogen that we're observing here to a hydrogen on an adjacent atom. The degree to which the splitting occurs is a function of the bonding. And so the bonding interaction between these two communicates the spin nature of the adjacent hydrogens on the adjacent carbon to the hydrogen that we're observing. So you should be pretty familiar with thinking about these fairly simplistic situations here where we have a singlet that has no neighboring hydrogens on the adjacent carbons, and so it's not split. A doublet where we are basically splitting that singlet intensity into equal intense lines here from one interaction. A triplet which has two adjacent hydrogen atoms, and then a quartet which has three. So in this situation here shown on the left, what we have is identical coupling constants, okay? That is, the splitting that occurs from each of the hydrogen atoms on the adjacent carbons splits it equally. So what this means is that the intensity of the center line builds up fairly rapidly compared to the outer lines because this degree of splitting is equal. So each time we split it, the lines overlap. Now, what we're going to see with aromatic compounds is that the degree of splitting becomes unequal for reasons that we'll get into in a second. But let's just talk about what this J value is. So it's a separation of two peaks here, and it's measured in hertz. So often we think about chemical shift as being in parts per million, which is a function of the magnet, the spectrometer that we acquire things on. But coupling is independent of that magnet. So we measure it in hertz, and it's a constant. So it should be the same on both sides. So if we see a coupling of this proton here, we should also see the same size of coupling on the other side. So we're going to be talking about situations where we have more complicated coupling patterns that's shown here on the right, where in this situation we have a proton that's coupled to two others, but the coupling constant is different from the first interaction to the second one here. So this would represent the first interaction, and then this particular situation would represent the second. And so what happens here is J1 is not equal to J2. Specifically, the second one is smaller, and so what this means is that the inner lines here don't overlap, and this produces a pattern referred to as a doublet of doublets. Okay? If J1 was equal to J2, we would end up with a situation referred to as a triplet here. Okay? So this is kind of summarized on, this little slide here, where again, we're just kind of looking at what happens as we make one of these coupling constants different for, particular bonding orientation reasons. Again, if we started off with a quartet for this hydrogen that we're observing here, and if for some reason the coupling constant to H1 becomes slightly different than the ones on this methyl group, we can transition this into a much more complicated pattern. This pattern here, if we have, again, our coupling constant slightly smaller than the other one here, non-equal, what we would end up producing here is a situation called a quartet of doublets. So the larger splitting represents the quartet value, and then the smaller splittings associated with this multiplet would be the doublets. Now, one of the things to always realize here is that when we're looking for these coupling values, we want to be looking for the distance between the first two outer lines as a true coupling. Okay, so in a first order multiplet, so a situation that we are able to basically interpret with our eyes, and we don't have to use any fancy computer simulations here, the distance between these two first outer lines will always be a true coupling. So if we can measure that distance, we can then find it in the rest of the pattern. Okay, so that would be the same distance here, and the same distance here. So in this little coupling tree up here, if we collapsed and took out that little coupling pattern, we would be left with a quartet. Okay? And to measure the quartet value, what we would have to do is make sure that we are measuring from different parts of the quartet that are the same. So we would want to measure from this line to here. Okay? Since this little peak here is a doublet, we would want to measure the intensity from this line to this line, because that would represent the two lines that make up the outer part of our quartet. Similarly, we could measure from this line here to this line here, and that would represent, again, another part of our quartet, and we should get the same value of 6.6 hertz for our quartet coupling. Okay? Because each of these parts of quartet are split into these doublets here, we could also get the same number if we measured from here to here and here to here as well. Okay? And so that's how we kind of analyze these first order multiplets. Now, what about aromatic signals here? So you have had some experience already in looking at aromatic signals on monosubstituted benzene. And this spectrum may look familiar from your POCUS. So first off, let's look at how we could categorize each of these particular signals. So again, if you use a shorthand nomenclature, we could start off by calling this signal a triplet. So just with a simple lowercase t. Same thing with this as a triplet. And then this one here as a doublet. There is a little bit more going on here for reasons that I won't go into, and we'll look at how we would analyze a little bit more with this particular sample. Now, if we focus on this particular signal right here, there's a little bit more that we can glean from it, particularly if we ignore now this bigger triplet coupling that we've accounted for. When we look at the smaller one, we can see that it is a smaller triplet. So I'm going to call this a triplet of triplets. Now, it's somewhat obscured here because there's some broadening that's associated with each of these little signals here. So we're not going to be able to fully interpret this, but it looks like there might be the possibility of another coupling within each of these signals here. So let's focus on interpreting what that triplet of triplet value could mean here. So like I mentioned, this is an aromatic system. And so one of the things that's important in interpreting the structure of organic compounds for aromatic systems is because all of these systems are sp2 hybridized, they all have pi bonds between them, which increases the amount of electrons, which increases the distance to which coupling occurs within these systems. So typically the J3 value is something that we think of as a hydrogen on an adjacent carbon here as something that we could measure in most sp3 systems. But in an sp2 system, we can often get information from J4 or even J5 values. So that is systems that we could think of as being meta to one another, or protons that are meta to one another, or 1,3 on the ring is another way of talking about that, is something that we can think about for this. So often what I do is, instead of focusing on specific numbers, I often think of the fact that in aromatic systems, we should have a large coupling, a small coupling, if we have adjacent neighbors that are meta. And unfortunately for the para systems, we often see near zero coupling for these para systems. This happens to be the fact that, this value is fairly small and it's pretty close to what the width of this particular NMR signal typically is. So it's harder for us to measure with a simple 1D NMR value. So let's look at how we would interpret this particular signal here that I labeled a triplet of triplets. first let's determine what the relative sizes of each of the couplings are. Well, my first part here is the triplet, which represents the large coupling. And so what we have here are two large couplings, which makes up the triplet signal. All right. And then from the other triplet, I have two small couplings. All right. So let's look at how we could create a part structure to explain this signal. So I would have my aromatic ring here. This is the hydrogen I'm observing. And now, to account for my two large couplings, I have to have two ortho neighbors, because ortho hydrogens to one another produce large values of splitting. And I'm going to also have two meta neighbors, because meta neighbors produce smaller coupling values. All right. So in my part structure to explain this triplet of triplet signals here, I should have a hydrogen here, which has two ortho neighbors and two meta neighbors. I can't really determine from my analysis of this signal if there is a group here, okay? So I'm just going to put a little broken bond across that because I don't have any information that I am extracting from this signal to tell me or provide any insight into what this could be, okay? If we look at this signal, and what this implies is that we should have another hydrogen here in a situation where it also has two ortho neighbors, right? That would also have maybe smaller interactions to one particular side. And if we think about this triplet here, which has a large splitting here, it would have two ortho neighbors, right? And then there's a smaller something happening to this signal here, which implies that it probably has an additional small coupling that we're not able to resolve, okay? So let's return ourselves to this little signal right here, which is a doublet of doublets. And so this smaller splitting here is also a little doublet. We have a large doublet, so we have one large coupling value and one small coupling value. And this would actually fit for the hydrogens here that are in this part structure. So we could redraw another part structure to explain this, but this would essentially imply that we have one ortho neighbor and one meta neighbor. We could potentially have two meta neighbors here, but if this situation was symmetric, it could be that these two signals don't or are identical. So this is actually the spectrum of benzoic acid. This is something that you guys have already interpreted in the oxidation lab here, so you should be actually familiar with this, and that should make some sense. Now, where things get interesting is when we look at disubstituted benzene patterns. So these are the different structural isomers associated with the three different isomers of iodo-phenol. And so looking at these, there's a couple of different possibilities that we have, but essentially for two of them, we could distinguish it from the third in that they should each have 4 peaks. So for the ortho isomer, the meta isomer, and those, they should each have 4 combined peaks. And that's because if we think about this, there is no symmetry associated with each of these rings. The para isomer is different in that there is a plane of symmetry through the molecule, okay? So the hydrogens on the left side, as it's oriented here, and the right side are the same. So what this produces is essentially a hydrogen in each case that has one ortho neighbor. All right, and so we get doublets. Now I put doublets in quotation marks here because if you zoom in, there is some very small, fine patterns associated with these signals. They look like maybe if you squint, they could be triplets, They're not actually triplets. This is an instance of some non-first order behavior, but this particular orientation of the signals is pretty indicative of a para-substituted isomer. The intensities, if we think about this in terms of how a triplet should look from a 1 to 2 to 1, don't really bear out for this particular signal if we try to interpret that finer, smaller coupling associated with it. So for the rest of these, we should be able to interpret this, and this is part of your worksheet here, according to that kind of example that I had before, where we're looking at what the splitting pattern is associated for each of these signals and drawing out some part structures to assign this. So I'm not going to go over these in explicit detail because they are part of the aromatic review worksheet that you guys have been assigned. But a lot of these should make sense if we think about the fact that if we look at one of these protons here, we could be able to think about whether or not it should have a couple of ortho neighbors and whether or not it has any meta neighbors to explain the patterns that we're seeing here. So for distinguishing these two isomers here, we would really be looking for what the coupling patterns are that are associated for the different signals that we see in the NMR, and we can unambiguously assign the spectra of each of these. So let's look at another one that really looks at, kind of some of the different possibilities here. Again, if we were looking at each of these signals and we had this pattern here for these different possibilities, we could easily assign one of the substitution patterns to this particular signal, or to this particular NMR spectrum here. So for one, we can ask ourselves just how many signals there are. So we would have 1, 2, 3, and 4. Now 3 and 4 are pretty close to one another, but you can see that this particular pattern here is pretty similar to the pattern here. Same thing with that one. All right. So since we have 4 signals associated with this NMR spectrum, we can already rule out that it cannot be the para-isomer, because the para-isomer should give us only 2 signals in the NMR aromatic region. Now, as determining which one is which, we can interpret some of these patterns. So let's just look at what we are learning from this signal here. I'll give you a second, and you can see if you can determine what the pattern is that we're looking at. So if we look at this, I would first look at the smaller splitting, and I would say, well, I have a little doublet, and it's also mirrored on the other side of this pattern. So I have a small doublet, and then I also have a larger doublet, okay? So I would call this a doublet of doublets. And again, in my just simplistic thinking, I have one large value and one small value, okay? For the worksheet, we're going to want you to put actual numbers on this from subtracting the numbers associated with each of the peak picking values in MNOVA. But this is how you can shorthand begin to think about interpreting this data. So again, if I think about a part structure associated with this, I'm going to have a proton that I'm observing, and then I should have one ortho neighbor, so I can't have another ortho neighbor on the other side, and then I should have one meta neighbor to give my one large coupling on the order of 7 to 8 hertz, and one small coupling on the order of 2 to 3 hertz. All right. Now, again, I also know that I can't have another meta neighbor, so I have to put a Y value associated with that. Now, I don't have any information as to what would be para to the signal again, because we don't observe couplings associated with that particular signal in 1D NMR. All right. So that's my part structure here. And the way I have it drawn, it seems to strongly imply that I have the ortho isomer here and not the meta isomer. But we should always interpret all the signals before making that definitive conclusion. So let's take a look at signal that I've labeled here as 2. So how would you assign the multiplicity of this particular signal? what would you think the small coupling is, and what would you think the large coupling is? All right, so hopefully what you got for the large coupling was a triplet, and for the small coupling, it should be a doublet. All right. So again, coupling values are always reported from the largest to the smallest. That's the convention. So again, I should have 2 large couplings here and 1 small coupling. I don't know what the values are particularly in this compound, but just to show you how you would write this out, you would say J equals, let's say 8 and 2 hertz. Okay? You don't have to repeat the 8 number twice to indicate that it's a triplet, because that is implied in this triplet particular value here, that 8 coupling gets applied twice. So let's think about a part structure for this particular signal here. So again, I would have proton that I'm observing, and based off of my interpretation with this particular signal here, I should have 2 ortho neighbors because I have 2 large coupling values, and then I should have 1 meta neighbor. Now, I know that there can't be something meta, and I can't tell anything about the fact of what I have there being paired. Okay? So just by interpreting these 2 particular signals here and drawing part structures, I can pretty definitively assign that the structural isomer that I'm looking at here is the ortho one, because this particular part structure shows to me that I have to have 4 hydrogens essentially in this particular pattern on the ring. With this one, I knew that I had 2, and if I look in the rest of this NMR spectrum here, I would get the same part structure for this particular triplet of doublet signal, and the same thing for the doublet of doublet over here, which would fit for all of the 4 unique protons on this particular ring. Okay. Now, there's one last topic I wanted to just go over here, and that has to do with the chemical shift of aromatic substituents. Typically, this is something that I look at after I look at the coupling patterns, because the coupling patterns are much more definitive about what the bonding information is. So the way to think about a lot of these is, aromatic species have the ability to have different resonance form with things that are pi donors or pi withdrawing groups. So species like this phenol here, or things that contain oxygen, or things that have heteroatoms off of the ring, can participate in resonance with the particular pi bonds in the ring. The same thing can happen with groups here that have pi bonds right off of the ring, such as a carbonyl or, say, a nitro group. If we think about what the Lewis structure is for a nitro group, we have this particular resonance form here. And so what can happen with these groups is these would be referred to as electron withdrawing groups, and these would be electron donating groups, okay? Because we can actually donate this electron density into the ring. So with an electron withdrawing group here, we can actually pull electron density out of the ring by, let me just change the color, pushing the electrons onto this nitrogen atom and up onto this oxygen here. To pull electron density out of the ring. So what this does is it actually ends up producing different values on the ortho and meta carbon. So for electron withdrawing groups, we tend to decrease the electron density at each of these sites, and for electron donating groups, we tend to increase the electron density at the ortho and para sites. So what does this mean? Well, this means that for those particular positions, we end up either increasing the chemical shift. That is, so when we reduce the chemical, density off of those, we end up causing it to move. So when we end up decreasing the electron density, we end up causing it to move to values higher than 7.36. And then when we increase the electron density at the ortho and para sites, we end up decreasing the chemical shift below that. So that makes sense in the fact that we are increasing the shielding at those sites, and it's becoming closer to TMS, which we think of as our zero reference, which is a highly electron-rich base system. So to just show you a little bit of an example of what's happening here is, if we look at a system like this aniline type system where we have this nitrogen electron donating group into the ring, most of the chemical shifts of these signals are lower than what we would just think of as a neutral benzene molecule here. And you should be able to determine which ones are the ortho and para protons on this particular ring from the coupling constant values and from the pattern values that we have associated with here, but it should be these two signals here, okay? Now for the meta ones, what we end up doing is we end up with, again, withdrawing a lot of the electron density off of the ortho and para sites, and so the ortho and para systems end up being shifted higher up above that. Now, I usually interpret this last and make it for my fine assignments because there are some inductive effects that can happen here, and each of these cases, we basically are assuming that the meta hydrogens on these carbons don't change too much, but you can see there is some inductive effect that's happening in each of these cases for these meta protons because that is shifting slightly around. The pi effect is a little bit larger, and so there is some movement, larger movement among the ortho and para protons associated with this. But this is, again, something that you don't have to, I wouldn't start with as a way of gauging things. Now, the other word of warning I'll say is that, when chemical shifts are separated as they are on the left here, these types of systems are really easy for you to interpret. You should be fully aware of how to interpret these things, and you should be able to assign all of the signals to the hydrogens on this ring. Now, there are situations where the chemical shifts of all of these protons become nearly identical, and they all begin to overlap, and they produce second-order effects. So there's complex quantum mechanical effects that can happen here, and what this means is we just have to refer to this as a multiplet, okay? Because there isn't any way for us in a simple first-order approximation way to interpret this particular value here. Notice that these two things are structural isomers here, and so what's happening again is that we are changing, the orientation of the relative groups on here, which ends up changing the chemical shift around of the particular proton. So the particular protons that we're talking about here are, different from one another, and they're causing them to shift around between these two different isomers. So hopefully that helps. I'm going to put a link out in the email to you guys as well to a little bit that you can read about coupling. It's from a graduate course that my graduate advisor did. There's a little bit parts of that there if you guys want to know more and you're still confused and you don't, learn from just kind of listening to me talk about this and run through some examples. Maybe reading through that would help you some. All right.